So I think everyone's got their coffee, so we're going to start. It's 11 after, so 5 minutes. So I'm Tony Lyons. I'm with the Center for Coastal Ocean Mapping, and I get the pleasure of introducing Jenna Hare today because she's my postdoc. I've been seeing, she's been here since October. I've been seeing what you're going to see today in 45 minutes over the past 6 years. 6 years. She had a great advisor, so I met Jenna for the first time in 2017 at a conference in Greece. Where was that? On some Greek island. Enjoyed the talk, so I think the first part of this you're going to show. In 2019, I met Jenna again at the same Greece conference. I missed her talk then, but we met in the Munich airport and she gave me a one-on-one showing, I think, of this stuff. Let's see. Jenna graduated with a PhD from Dalhousie University, which is in Halifax, Nova Scotia, in 2021, which is interesting. My son is now there, so there's some sort of conservation law, and some we have to trade people. The work you're going to see in her PhD work is really using, as you can see, acoustic measurements to determine something about the oceanography. For me, for the postdoc, which I think you're going to show a couple slides at the end, she's using changes in the oceanographic parameters to sort of predict, or seafloor properties to predict changes in the acoustic. So she's come full circle now. She's at one end of the spectrum. So with that, I'm going to leave it to you, Jenna.
Thanks, Tony, and thank you everyone for showing up. I know there's a lot of snow this morning, so maybe the roads were the greatest. But as Tony said, I'm going to talk mostly about my PhD work that I did at Dalhousie with Dr. Alec Hay. And we were interested in using acoustics to measure gravity-driven granular flows underwater. So granular materials are really important for many types of different types of flows, such as avalanches, debris flows, turbidity currents. And their dynamics are actually quite complex and nonlinear. There's a lot of interactions going on. And so there's still no accepted set of governing equations that fully describe their complex behavior. And that's why more measurements are needed to really understand what's going on. In the ocean, the transport of granular materials, or mostly of sediments, impacts a lot of different things, such as the shape of the seafloor, bed form dynamics, the stability of the coastal infrastructure. And so it's important to understand how the movement of sediment can impact these different things. And so of particular interest to me is bed load, which is the part of the total sediment load that that moves in somewhat continuous contact with the bed, as opposed to the suspended load that travels more in the water column. Video here. And so making measurements of bed load, what you need are velocity measurements of the grain and concentration measurements. And those are difficult to measure, especially understanding or measuring the velocity structure within a thin moving layer of high concentration sediment. And so optical measurements that are looking through sidewalls in the lab are often compromised by sidewall friction. And so that's why there's been some promising work done with using acoustic systems. So these are pulse-coherent Doppler profiling systems. And because they use really high frequencies and short pulse lengths, you can achieve really high range resolution with these systems. And importantly, the measurements can be made remotely, so away from any tank sidewalls in the lab. So let's look a little bit at this non-invasive geometry for acoustic remote sensing and the types of things that we can learn from it. So here in this sketch, I've got a transducer that sends out some pulse of sound that'll travel down the water column based on the sound speed in water, which is relatively well known. And it'll then interact with the bottom, with the sediment at the bottom, and part of the signal will be reflected, and so there's a reflection coefficient that can provide information on, and part of the signal will be transmitted through the water saturated sediment. And so the depth of penetration of the signal, or the attenuation coefficient, is a parameter that's important, and then the sound speed within the sediment is also important. And so when you pair that with more transducers angled at an angle, you can then get an idea, you can then potentially measure the sediment velocity in transverse direction of the transducer. So that's kind of the different things that I'll be looking at in this talk. And so the overall goal of my PhD work was to use acoustic remote sensing technologies to measure the velocity structure within a thin, high concentration moving layer of sediment. And so to first do that, you really need to understand how this high frequency sound interacts with the sediment underwater when the sediment is stationary. And so the first part of the talk investigates the frequency, grain size, and concentration dependence of the depth of penetration of the signal or the attenuation, the phase speed, and then the reflection coefficient at the sediment-water interface. And then in the second part of the talk, I'm going to look at the granular flow measurements, so investigating the grain size and roughness dependence of the velocity structure within a thin, high concentration moving layer of sediment. And so the grains sizes that I'm going to use and the grain types I'm going to use throughout the talk, I had measurements for 2 sizes of sand and 1 size of glass beads. And as you can see from these scanning electron microscope images, the glass beads are a lot smoother and rounder than the angular pieces of sand. So parameters that will come up throughout the talk are the grain radius, A, the density of the sand and the glass beads, which are slightly different density, but similar-ish. Concentration by the surface roughness of the grades, and then the roughness of the sediment-water interface. And the frequencies of interest are very high frequencies from 1 to 2 megahertz. So that means that the wavelength of the sound here, kind of illustrated on these images, is comparable to the grain size. And so what happens is that the physics gets really interesting, as you'll see. And so an important number that I'm going to use throughout the talk is the acoustic wave number, K, which is proportional to the transmit frequency and inversely proportional to the wavelength. And if you multiply that by the grain radius, you get a non-dimensional parameter, Ka. And so a lot of the plots you're going to be seeing are going to be plotted as a function of Ka. So in this first part, this was looking at the depth of penetration of the signal and looking at the dependence on frequency, grain size, and concentration. So here I've plotted measurements reported in the literature for the attenuation coefficient as a function of this non-dimensionalized wave number K that we just saw in the previous slide. The squares that are white are measurements reported for glass beads, and the squares that are blue are measurements reported for sand. And you can see that there's a general trend as frequency or increases or grain size increases, the attenuation also increases. And you can divide this plot into 2 sections. At the lower frequencies, the longer wavelengths, the attenuation of sound is mainly due to viscous losses. But the high frequencies where the wavelength of the sound is similar to the grain size, scattering becomes really important. And here I've plotted on top Schwartz and Plona's multiple scattering theory that predicts the dependence of the attenuation coefficient on K to the 4th, or frequency of the 4th. So a much different dependence than what you see here down in at the longer wavelengths. And so all of these measurements that are reported in the literature were made using a 2 transducer setup. So one transducer that sends out pulses of sound and another transducer a certain distance away. And by varying the distance between those 2 transducers, you can get the attenuation. And that's all great. But the kind of measurements we want to do using kind of a remote, non-invasive setup. And so we wanted to see if we could make measurements using one transducer, what that would look like. So our setup had a transducer that would send out pulses of sound, travel through the water column in different thicknesses of sand, hit some kind of reflective surface and come back. And looking at the change of the signal through different thicknesses of sand, we can get the attenuation coefficient. And so that's what I plotted here, these circles. So for different colors for the 2 sand sizes and glass beads. And they're followed very nicely using are very comparable to the literature measurements, and also follow this K to the 4th dependence predicted by Schwartz and Plona's multiple scattering theory. And so that was great. We're happy. The non-invasive geometry is validated, and these attenuation measurements will come up later in the talk. Will have some importance then. The other thing we kind of wanted to understand is the dependence of this attenuation of sound on concentration. So here we're looking at the same data. The data from the previous slide are all in gray here. And the attenuation is a function of wave number, both multiplied by the grain radius. And then our measurements are the ones are the gray circles. Now, all those measurements were made at a concentration of sediment that's pretty much similar, all at about 0.6 solid volume concentration. And so in the literature, we've also found measurements where the concentration was varied, and going from like very dilute suspensions almost to much more compact suspension. And clearly that has an effect on the attenuation of sound. You can see there's a fair bit of scatter among the reported measurements. And so if you take that plot and divide by the solid volume concentration, everything collapses quite nicely onto this one curve, showing the importance of measuring concentration, which isn't always reported, but also that to first order, the attenuation has a linear dependence on concentration, which will come up again with the talk. That's for the attenuation. We wanted to look at now the phase speed in the water saturated sed and glass beads, and look at the dependence on frequency, grain size, and concentration again. So I won't spend too much time on this part, but here we've got phase speed within the water saturated sediment, normalized by the sound speed in water. And again, plotted as a function of this non-dimensionalized wave number. And so the squares are the measurements from the literature. Again, sand being the blue squares, and white are measurements for glass beads reported in the literature. And our measurements here are plotted with the circles. I've also plotted on top Schwartz and Fulmer's multiple scattering theory for my grain sizes. And so first off, you can see that there's a decrease at these high KAs, so higher frequencies and larger grain sizes. The sound speed actually decreases with increasing frequency and grain size, coming closer to the sound speed actually in water. So this negative dispersion has been observed before, as you can see in some of the literature. We're just kind of extending a little bit those measurements. But what we found is that the scatter can be partially explained by the differences in concentration of the measurements as well as the density. So here I've scaled the data by a factor that depends on the density of the sand, the water, and then also the concentration. And that reduces the scatter a lot between especially our measurements have collapsed, and then some of the other measurements have kind of collapsed on themselves. So the take-home message for this part was that that negative dispersion, we observed that as well, and really this data collapse under size scaling, showing the importance of concentration and the dependence of sound speed on concentration. So next we're going to look at, we've been focusing on the measurements within the water saturated sand sediment, but now we'll focus on what's going on at the interface. So again, looking at the frequency and grain size dependence of the reflection coefficient at the sediment water interface. So here I plotted reflection coefficient as a function again of Ka. And this is the prediction for a smooth surface. So that's just based on the impedance contrast between the water and the sand. So based on the sound speed in the sand and the density, or I say sand, but I also mean glass beads of the sediment. And so this is decreasing with Ka, and that's only due to that negative dispersion that we'd seen before. And so we made measurements using this monostatic setup, one transducer, looking at the backscatter return from the sediment water interface. And here are measurements for our glass beads in yellow, and then the sand and the two sand sizes and blue and purple. And that clearly does not follow this smooth surface prediction. But that's because at the frequencies we're at, and at the grain sizes we're at, the wavelength is comparable to the grain size. And so the surface is not smooth to the sound. So here, I took images of my sand surface, glass bead surface, looking kind of through a sidewall to get an estimate of the roughness of the surface. So I extracted the sediment water interface here from these images, and from that could calculate a roughness estimate of the surface. And if I multiply the smooth surface prediction by a factor proposed by Eckhart, which depends on the wavelength of the sound, the wave number, and the roughness of the sediment water interface, that actually decreases a lot more rapidly than the smooth surface prediction and follows the data a lot more closely, which was makes a lot more sense to us, obviously, than the smooth surface prediction. So there are measurements here reported in the literature. Unfortunately, none of these measurements report surface roughness, but you can see that they all decrease, most of them all decrease a lot more rapidly than the smooth surface prediction. The take-home message for this part was that the Eckhart rough surface model accounts really for much of the observed size and frequency dependence of the reflection coefficient. Again, showing that once you're at these high frequencies and larger grain sizes, the physics gets a lot more interesting. So these are all measurements, kind of independent reflection coefficient measurements. We wanted to see, does the reflection coefficient depend on the position of the transducer relative to the surface? So for these measurements, we have our transducer looking at some patch of sediment, and then we move it slightly in one direction and make another measurement, and then move it again and again, and so on and so on. And here are the results. And this initially was surprising to us, but then we figured it out. So in this top panel, I've got acoustic range to the sediment water interface. And this is position, horizontal position that we're basically moving to transducer. And acoustically, that surface is flat. This is, just to give you an idea of scales, is 1 grain diameter. But if we look at the backscatter amplitude as a function of this horizontal position, here I've plotted for 3 different frequencies to just offset the vertical so we can see that more clearly. We're seeing these oscillatory variations in the backscatter amplitude that is not related to any variations at the surface. And so we wanted to try and explain this. We decided to create this simple single scattering model. So in this model, I've got a transducer looking down at a surface of grains. The grain sizes, the model grain sizes are based on my measured grain size distribution. And I displace the grains a little bit in the vertical based on the roughness of the interface that we've measured, I've shown previously. And all I do is sum the contributions from each surface, from each grain back to the transducer, and assuming a circular footprint of the transducer. So looking at that, this is the modeled backscatter amplitude, just in arbitrary units as a function of horizontal position of the simulated transducer. And we're also, in the model, it's also reproducing these kinds of oscillatory variations with similar length scales. And so that was great. The model reproduces the observed oscillatory variations and the associated length scales, as I said. And the decorrelation length scales are about 20% of the transducer size. So that means that to be able to make independent measurements, you have to move the transducer more than 20% of its size to actually make a lot of independent measurements. You can't make measurements too close to each other, or else they're not independent. And so based on the model, we can say that these oscillatory variations are due to the interference among these scattered waves. Okay, so that kind of concludes the first part of the talk, where we're dealing with stationary sediment, looking at the geoacoustic properties of these sediment. The second part of the talk was looking at granular flows. So here we wanted to investigate the grain size and roughness dependence of the velocity structure within a thin, high concentration moving layer of sediment. So here's our setup. I have a chute that's submerged into a much larger tank of water. It's 60 centimeters long, 15 centimeters wide, and the bottom of the chute is made rough. At upslope, at the upslope portion, there's a cofferdam. We've got a gate here to hold that cofferdam in place, and I pour the sediment. Either here, I'm going to be showing results from the coarse sand and from the glass beads. So I pour the sediment into this cofferdam. The cofferdam is removed, and the sediment flows along the bottom in a nice, somewhat nice layer with a thickness of only about 1 centimeter. So we're really looking at very small scale stuff here. And these first set of measurements are going to be surface velocity measurements obtained using a camera. It's a high resolution camera, taking frames at 120 frames a second. And so using a particle imaging velocimetry, PIV, we can get the velocity structure of the surface velocity across the chute. I'm also going to compare these measurements to a pulse-coherent Doppler profiler. They can just buy off the shelf a Nortec Victrino, and that operates at 10 megahertz. So, and they're located it's about 20 centimeters from the gate. So kind of in the middle portion of the chute, away from the sidewalls. At least the Victrino is away from the sidewalls. The camera has different positions, as you'll see. So first we'll look at one of the movies from the camera. Just to situate yourself on the vertical axis is a position, downslope position from the gate. And then on the horizontal axis is distance away from the sidewall. So we're only looking here at 3 centimeters close to the sidewall. And this is after the front has passed, so a couple seconds in, once kind of steady flow conditions have been obtained. And this is played back at quarter speed. I find these movies are pretty, definitely spent a lot of time looking at them. But what you'll see is that the grains are moving a lot more slowly. Again. The grains are moving a lot more slowly right at the sidewall compared to further away from the sidewall. And that's due to sidewall friction, as we'll discuss. So here are the results of, so this is downslope velocity, U, as a function of distance away from the chute sidewall. This is just surface velocity. I'm averaging over 3.5 seconds and over 3 repeat trials. And the camera was positioned in one spot that was closer to the chute sidewall, and then in another position a little bit further away from the sidewall. Yes, okay, and then the Victrino measurements are just point measurements, these circles. Here are the 2 positions. So first off, it's very nice to see the PIV and acoustic measurements of surface velocity agree quite well. You're also seeing a sidewall boundary layer. That's not surprising. We know the sidewall will affect the flow of the grains, and you could see that from the movie. So there's much slower velocities right at the sidewall, even like almost like 1 centimeter a second, compared to about 10 centimeters a second. More in the middle of the chute. So now that we've got the surface velocities, we understand that a little bit more. What we really wanted to get at is the velocity structure within the moving layer and away from the chute sidewalls. And so to do this, I'm going to use our pulse-coherent Doppler profiler. We call it the MF-Dop. This was developed and built in-house by my supervisor over many years, and this is just one version of it. So it's composed of a center transducer that has transmit and receive capabilities, and then 2 outboard transducers that will have receive only capabilities. The transmit frequency that we used was 1.2 megahertz and a very short pulse of 1.5 microseconds. So allowing us to achieve really high spatial resolution of about 1 millimeter. Yes, and then so using the MF-Dop, we can obtain 2D velocity profiles from the rate of change of the phase of sound scattered from that fixed from a detected volume in a fixed range. So back to our setup drawing. Here's our MF-Dop. We're going to get a velocity profile through the moving layer, downslope from the gate again, and away from the chute sidewalls at 1.2 megahertz. And I'm going to compare that velocity profile to one obtained by the Victrino. That's the acoustic instrument that off the shelf that you can buy at 10 megahertz. And then a camera looking through the chute sidewall at like it's the same camera, so 120 frames a second and high definition. It's got another movie for you. So this is after the front has passed, played back again at quarter speed. And so the thickness of the, in this case, the moving layer is about 6 millimeters to give you an idea of scale. And so you can clearly see that the sediment right at the bottom is basically not moving. And then as you're moving up, the sediment is moving a bit faster. But you can also see that the sediment, kind of blurry sediment away from the chute sidewall is moving a lot faster than the sediment right at the chute sidewall. So I'll try that again. Yeah. I just like these are pretty. All right, so here's the backscatter amplitude registered by the MF-DOT for one of the sand trials. So here we've got time on the x-axis and vertical distance away from the chute bottom on the vertical axis. The color is backscatter amplitude, and in red, I've defined the sediment-water interface based on the backscatter amplitude. So at time 0, that's when the front is passing just right underneath the MF-DOT measurement position. And so that's kind of the front. And after a couple of seconds, you get a period where the thickness of the moving layer is relatively constant. And so for the rest of the talk, when we're looking at vertical profiles of velocity, they're going to be averaged over this 5-second averaging window where things were relatively in steady state. And so here's an example of one of those vertical profiles of downslope velocity. That's U, so downslope velocity, distance away from the bottom here. This is the measurement in blue is the MF-DOT measured velocity. It's averaged over 3 repeat profiles in that 5-second averaging window. And the thickness of the moving layer in this case was a little less than a centimeter. So that corresponds to about 23 grain diameters. And so you can see that the MF-DOT velocities tend to 0 near the bottom. That's no surprise because remember the bottom has a fixed roughness bed. So we were trying to kind of get this a bit of a no slip at the bottom. And you've got a maximum velocity within the moving layer. And so you've got these shear layers at the bottom and above that are about 6 grain diameters. And we can plot on top of that the velocity profile obtained through the chute sidewall by the camera using PIV, and that has a very different shape. The velocities are a lot slower, the thickness of the moving layer is a lot thinner, and the shape is different. And that can all be attributed to this the sidewall friction and boundary layer that's created by the sidewall. So those are the sand measurements. In the next slide, we're going to look at measurements for the glass beads. So in blue are the MF-DOT measurements, and this time I'm going to compare to the Vectrino measurements. So we got downslope velocity again and distance away from the bottom on the vertical axis. Now both instruments agree pretty well with the thickness of the moving layer, so that's great. And they also agree fairly well with at least the velocities and the shape of the velocity profile, tending to 0 velocities within the water column, this kind of negative shear layer here at the top of the moving layer, and a maximum velocity within the moving layer. Now, importantly, the Vectrino transmits at a much higher frequency, 10 megahertz, compared to the MF-DOT's 1.2 megahertz. And if you remember from the beginning of the talk, I said that attenuation is proportional to frequency to the 4th. And so the Vectrino's signal just does not penetrate very deeply to that moving layer. And so that's why I've kind of cut off the Vectrino profile here. And that's due to its higher transmit frequency. So now that we have this velocity profile, we kind of wondered, can we use what we know about physics, what we know about theory, can we use that to estimate the concentration within the moving layer? And so we turn to the Navier-Stokes, the momentum equations. If we make some very simple first order assumptions, We assume steady state. We neglect some nonlinear terms. We assume that the vertical velocity in the moving layer is close to zero, and that was actually verified by our measurements. And importantly, we're just going to assume to first order uniform concentration through the moving layer. And so that means that that momentum equation reduces to two terms. It's the gravity balanced by a friction term. So the gravity term depends on the angle of the chute, the density difference between the sand and the water, but importantly, on the concentration of the moving layer. And the friction term here depends on the effective viscosity of the moving layer and then the shear, the velocity profile. And so if we use the boundary condition that there's a velocity maximum within the moving layer and so that the shear is zero there, and we're going to just have a free slip at the bottom, the solution to that equation is a parabolic solution. It'll depend on three parameters. Zeta here has just collected the concentration and effective viscosity in one parameter. Zm is, Zm is the height of the velocity maximum within the moving layer, and U0 is the velocity at the bottom. And so if we do a nonlinear least squares fit of this theoretical simple model to the velocity profiles within the moving layers, we get really nice fits. So for these fits, we're using zeta, Zm, and not as free parameters. And so here I've plotted the velocity profiles that we saw earlier for the glass beads in black, and here is the velocity profile on the right for sand. And the only difference from the profiles we saw before is I've non-dimensionalized the vertical axis by the grain diameter. So the measurements are in black, the MF dot measurements in black, and this parabolic solution, the fit to the measurements is in red. And you're seeing quite nice R squares, R squared of 0.85 for the glass beads and 0.95 for the sand. So we're quite pleased that this simple model can reproduce the main features that we're seeing in the velocity profiles. So given that this is a free parameter from the fit, so we get a best fit zeta that again depends on concentration and effective viscosity, all we need is a relationship between the effective viscosity and concentration to estimate what those two parameters are at the moving layer. And we can turn to the literature for that. There's a lot of relationships proposed in the literature. And the one that I'm using is Zereg et al.'s empirical relationship. That's the only one I could find that was developed for negatively buoyant sediment. And so we're using that one. And so based on their relationship and the best fit from the parameters from the model, we get an effective viscosity for the glass beads, the moving layer of glass beads, that's 500 times larger than that of water, and for the sand, 1,100 times larger than water. And so we're thinking that these differences are likely due to the fact that the glass beads are a lot smoother and rounder than the angular pieces of sand. And our concentration estimates here make some kind of sense. They're slightly less than the measured concentration for the stationary sediments, confirming that the moving layer is high concentration, but slightly more dilute than stationary sediment. And so just as a reminder, these are first order approximations. So it represents a depth averaged effective viscosity and concentration through the moving layer. So this was great. We're like, oh, we've got some reasonable results. Can we actually use acoustics to measure the concentration through the moving layer? And so we decided to modify our setup to try and do so. So here we've got that setup that we've seen, the chute experiment, but I've added a well here that's about 15 centimeters long, a couple centimeters deep. And the well is filled with the same material that the moving layer is composed of. So we fill the well and I scrape it flat and then release the sediment, and then sediment will flow over top a bed of like material. So that's a lot more realistic to what we see in the field as well. And so I'm only going to show the MF dot measurements for this setup. And we installed a pinducer. So it's a very tiny transducer, 1.3 millimeter diameter. that will listen for the transmitted signal through the moving layer. And we're going to try and get the attenuation of the sound through the moving layer using that pinducer. Now, I just realized today when I drew this, you have to think that the pinducer is actually like underneath the MF dock. It's not at the sidewall. So you can use your imagination for that, but they are basically underneath each other. Okay, so here is the, we'll first look at the velocity profile. So this is what we saw before, is the velocity profile over the fixed roughness bed for the glass beads. And at Z equals 0, in the fixed roughness case, that was just the bottom of the chute. For the rotable bed, Z equals 0 corresponds to the top of the well. And so below Z equals 0 is where we had sediment. And so what we're seeing here is a reduced velocity at the velocity maximum, but also a negative shear layer that extends all the way into the well, which makes some kind of sense. Basically, this is saying that the particles above the well are entraining and making the particles in the well move as well. And so these next are the attenuation measurements from the pinducer. So here we've got amplitude, transmitted amplitude registered by the pinducer under the MF dock as a function of thickness of the sediment over the pinducer. And the triangles are the measurements over 8 repeat Class B trials. I've also made a measurement when there was no sediment. And so if you draw a line through these measurements, the slope of that line gives the attenuation coefficient through the moving layer. And so we're getting a value that is less than the measured attenuation through a stationary, through the stationary sediment that's shown at the beginning of the talk. And that's just to give an idea that would be given by the dashed line. I've also shown here what the attenuation in water, the slope of that line would look like. And so given a first order linear dependence of the attenuation on particle concentration, which is what we'd seen at the beginning of the talk, we can estimate that the concentration within the moving layer is 0.516. So this is 15% less than the concentration for stationary sediment. So this is consistent, the moving layer being more dilute. It's also 10% less than the model prediction. So I think this shows a lot of promise for this method. There's definitely a lot of scatter, and more measurements would be good to kind of improve that. But we were pretty pleased that we're getting results that make sense with kind of a new method to measure the concentration. And key findings of the talk, just kind of quickly summarize that. So attenuation and phase speed measurements, they agreed with Schwartz-Zamplona's multiple scattering theory. There's a collapse of the data in non-dimensional space, and we validated the non-invasive geometry for the attenuation measurements. For the reflection coefficient measurements, there was a decrease with increasing Ka, and that was due to the roughness of the sediment-water interface, which was consistent with Eckart's theory. And for the granular flow experiments, using the MF dock, we were able to get a velocity profile within a gravity-driven granular layer, which hasn't really been done before for gravity-driven granular, submerged gravity-driven granular flows away from the sidewall. And a fit to a simple constant density model really yields a first order estimate of depth average concentration within the moving layer. And so these results provide the necessary support for making acoustic measurements of sediment transport in bed load conditions. And so actually the MF DOP, a newer version of the MF DOP was deployed in the field just last summer. I was involved in that field experiment. So I'm really excited to see the results that come out of that, to see what bed load estimates we can get from a field deployment. And that was in Oregon, on the beach on Oregon. So before I end, I just want to take a couple slides to talk about the current work that I'm doing here at UNH with Tony. So this is taking a step back at a much larger spatial scales and temporal scales. So in the ocean, the performance of active sonar system really depends on the acoustic properties of the seafloor, which Tony mentioned when he was introducing me. The problem is that the acoustic response of the seafloor is often assumed to have no temporal dependence. And we know that that's just not true. The seafloor properties are constantly changing, being influenced by fluctuations in near bed hydrodynamics or biological activity, and that can occur over a wide range of temporal and spatial scales. And so the overall research question for this project is, how do these changes in acoustic scattering from the seafloor relate to the environmental variability over daily, weekly, and seasonal periods? And so here's the data set that I have access to. So we have 2 years of data, 375 days of data collected over 2 years for 2 sites near Portsmouth, a wave-dominated site and a tidal-dominated site. And this, so basically the data are from a tripod placed on the bottom of the floor with 3 transducers, downward-looking transducers on it, angled at about 20 degrees grazing angle. And these transducers operate at 3 different frequencies. Also on the tripod, there's a CTD measuring waves and things, and cameras as well. And so here's just some preliminary results. This is the only plot I'm going to show for this. It's very much still a work in progress. But here we've got scattering strength as a function of time for one of the deployments in 2020. And here we've got significant wave height as a function of over that same time period. And the different colors are the scattering strengths from the 3 different transducers. And these are the solid line are daily averages, with the gray being a confidence interval. And so, as you can see, it is not constant with time. There's variability, things change. One of the things that are striking right off the bat are these are changes in scattering strength that occur for a couple of days, about 5 to 10 dB, that coincide with episodic storm events. So I've highlighted 2 of them here in this plot. You can also see that there are likely monthly or weekly trends. So here we've got a lower scattering strength and then a higher scattering strength after this one storm event. So those are all things that I'll be investigating. Also looking at getting bottom bathymetry using the phases from the split beam 70 kilohertz sonar. I mean, all in all, there's tons of data. That's basically why Tony was here. He's like, I have too much data, come analyze it. And I'm very excited to really be digging into this and seeing what we can get out of it. So I'll happily take any questions, but also leave my acknowledgement slide up because I'm very grateful, obviously, for all the support I've gotten in doing all this research. So thank you.
So for your PLE measurements,
Yes.
are you doing them on the sidewall?
Yeah, so the optical measurements on the side were through the sidewall. The MF dot measurements, spectral measurements, were all in the middle of the chute. So that's why those, if we go back, those profiles look different. Yeah.
Sidewall.
Here, yeah. So this is in the middle of the chute. This is right at the sidewall.
Are you using actual PIV or particle tracking? What?
It is PIV. I have images. I extracted all the frames from the video. I broke up each frame into little squares, I guess, and then looked at the intensity changes between each subsequent frame in that square, and then saw how those changed.
Statistical techniques like cross correlation.
Yeah, cross correlation in that like interrogation area.
So you're getting a lot more information out of that. Just
Yeah, well, I get 2D velocity from that. I've only shown the one the downslope velocity. Is that sorry?
yeah, okay. Yeah, I was going somewhere about like, do these measurements confirm the assumptions you're making for your theoretical analysis? It doesn't really connect that way, so never mind.
Okay.
But one other comment I had real quick is if you go back to slide 10, you said it collapses real nicely.
A lot of clicks. Yeah. All right. Yes.
10 on the right, you say it collapses really, really nicely, but it's logarithmic. And
Yes.
go to slide 13, and you said it collapses.
It's not. Oh, this one.
Yeah, another one with like only two or three. First, you said it doesn't collapse, but if you put this on a log plot, it collapses very nicely too, right?
Sure. Yes. No, I agree. I think there's definitely collapse in a lot of the scaling. It reduces the scatter, but it's not perfect.
So the collapse is meaningful because you have multiple layers.
Yeah.
That's just Martin's strategy for keeping all the data on the same figure.
So definitely in this paper, we do look at the second order dependence on concentration and look at that as well. And so yes, I agree with your point. That's true.
I had a question. It was also about the PIV, and
Yeah.
I don't want to like harp on the PIV.
Oh,
I was
no,
curious
yeah.
about, did you have to like tailor your mixture of sediment to get a good enough contrast between grain sizes?
So I only did the PIV on the sand because the glass beads
Are all the same.
all the same. There was definitely, if there was more time, at some point you have to end the PhD. But there was a thought of adding some different like blue particles and doing that. But yes, the sand, it actually worked quite nicely with the sand because there was different colors and there's definitely like darker sand particles. So doing simple PIV gave estimates that made some kind of sense.
Your the very last pictures you had of field deployments, I guess. What sort of water depths are those deployed in?
Yes, the one I was showing you is 15 to 11 meters. Wait for a trying to 11 Star Island, the depth is at 11 meters. 22? Okay. And then the Newcastle is 11.
Shallow.
Shallow. Yes, yeah.
And then how far away are the sensors from the sand bed?
1.8 meters.
Thank you.
I was curious about, so you know how you had the well?
Yes.
Yeah, so is what you were saying that when you had the flow going over the top of the well, the bottom of the well was also like effectively,
Yes,
like
the
the
grains,
sediment in the bottom was moving as well?
the grains in the well were moving. Obviously, the grains closer at the top, closer to the top of the well are moving more than the grains deeper in the well. But yeah, we're showing that it, as opposed to fixed roughness where the velocity goes just to zero at basically the height of the well, this kind of the velocity, the grains are moving above or affecting the movement of the grains within the well.
Got it, okay.
Out at the same time.
I'd like to piggyback on that.
Yeah.
Can you show that picture again? The
Yeah.
one with the well, 'cause I'm curious about.
Making me click off here. With the well?
Yes, the velocity profile for the version.
Yeah.
So is the well depth 20?
It goes deeper, a little bit deeper, that's how far the signal went,
Oh, okay.
the acoustic signal. So yeah, I cut it off there, but goes a little bit deeper. The well depth, it's about an inch.
Okay.
But this is now in grain diameters. And
I'm sorry I wasn't here for all of this. Do you see, what's the phase shift look like as you go down through that?
in the acoustic.
As you go down into the erodible bed and you've got velocity measurements, did you also see a measurable phase difference? A phase shift? You know, typically oscillatory boundary layers can lead. I guess this was steady flow, right?
Yes. Oh, I see what you're saying. Okay, following you now.
Did you see any lag in the mobile thickness as it started to mobilize?
I really was only looking, this is an average over 5 seconds. And I did look at like 1 or 2 second averages throughout. It was,
So does it look like grain by grain, like layers of grains that are shearing off? Or does it look like there is some pressure gradient that is sort of liquefying things and the whole thing goes fluid at a similar time?
it's a good question. Not really sure. I think I only looked at these profiles and then I looked at profiles in time. They look pretty much the same, but the granular flow itself is not that long too. So we don't have that many profiles to compare to, and you are like,
Interesting.
yeah, I don't have to think about that. I think Jenna.
Was the rough paper that you have on the
Yeah.
chute bottom, is that comparative, or is the roughness of that comparative to like a hard surface you would see in nature? Like, could that be comparative to?
So it's like basically sandpaper that we glue on the bottom. If we didn't glue the sandpaper, the chute itself is very slippery, and so you just weren't really seeing a profile. Everything was just kind of moving at the same velocity, and that wasn't as interesting to us. Whether that's representative of what you find in nature, probably maybe something, I don't know. That's a good question. I'm not really sure. Ian.
Also talk Jenna. So I was wondering, like how this instrumentation method could be used. So as a way of like better like measuring sediment properties like concentration. You were talking about how that could be applied to getting like better propagation models for shallow water acoustics that might depend on things like attenuation with bottom interactions.
Yeah, well, I think you kind of said it there that it's important to make these measurements for those kinds of measurements. A lot of the concentration methods that I know exist are like are invasive. You're putting something into the granular flow, or you have to bury something or whatever. So it can work in the lab, it can work in certain situations, but you are potentially influencing the flow. So that's why we're kind of excited that this attenuation, you're still burying the conducer, but it could potentially be, it was interesting to us that we were getting some kind of reasonable estimate of concentration acoustically, which hasn't really been done that way before, at least to my knowledge. But yes, the field is a whole different beast.
Right.
But yeah, we have deployed the MF-DOP in the field before in this latest experiment. Pretty excited to see the results slowly come out of that. But you need a lot of the models that invert backscatter to concentration. You need to know the dependence of the concentration dependence of attenuation. So that's also why the stuff at the beginning of the talk is important when you're using those kinds of models as well. Does that answer your question?
Yeah, actually.
Okay, I feel like
That was good detail. Thank you.
Yes.
Did you use actual sandpaper on the?
It's called Gator Grip. So I think it's very much like sandpaper, but it's got a like sticky adhesive side, and you can get different grits. I mean, it's the kind of stuff that I think they put on the like stairs, and you don't want to like fall on that. So we just ordered that, and it was very convenient that apparently the side of my chute was exactly the width of one of them. But that I was surprised for, like, it lasted underwater, it did not come off for months.
You mentioned some cases early on, and then these two baby currents,
Yeah.
sort of same thing, density driven,
Yeah.
downslope. Can you scale this to lower frequencies, bigger scales to use in the field for baby current measurements? The reason John Hughes Clark goes up
Yeah.
to British Columbia every year, and he's imaging them on multi-beam
Yeah,
and similar instruments. So, could you
I think so. Yeah.
finish?
I mean, as you said, the physics are different. Like the flows I'm looking at are gravity driven, turbulated currents are density driven. So the physics are different. They're a lot finer particles. So, but the data for inverting, there's definitely models I know that invert the backscatter from turbulated currents to concentration. I think Alec actually has a paper with John Hughes Clark on that with one of his students, but he's mistaken. But I don't think they've ever used the MF-DOP for that. I think would be cool. Yeah, but big one, I don't think you need something else, but yes.
Okay, thank you, Jenna.